Okay, I think I'm recording now. Thank you very much. Okay. Okay, so now let's start by going to this example. It's a pretty nice little example, and it illustrates working with complex or phasor vectors. Okay. Okay, it happens to come from the Shen Kong book. I'm sure you can find similar ones elsewhere. There's a vector A. A just kind of stands for arbitrary, I guess. You know, I mean, it could be an electric field. You can kind of think that way, but it could be almost anything. But anyway, there's a vector A, and let's say in the phasor domain, it's unit vector x plus j unit vector y, two-dimensional vector. Okay. And first part of the example is let's just convert it into the time domain and see what happens. Now, I want to point out before I start working it that the most interesting thing about the example is that it's got two components, but one of them has a j in front. Now, what that means physically is that the y component is 90 degrees out of phase from the x component, right? Because j corresponds to e to the j pi over 2, right? So it's 90 degrees out of phase. Now, if I didn't have the j there, and it just said A is unit vector x plus unit vector y, then those two components would be in phase, and the electric field vector, or whatever this vector is, would just oscillate like along a 45-degree line. But because of the j, because of 90 degrees out of phase, something interesting happens, and we get this rotation effect, as we'll see. Okay? All right. But anyway, that's the goal. Find the corresponding time domain vector. Okay, so notice the notation, the regular, Times Roman math notation in the phasor domain, and what we call, or what I call, the hand script SF font in the time domain. Hopefully you downloaded those fonts, by the way. Hopefully. Okay, anyway. So time domain A is the real part of phasor or complex A, e to the j omega t, right? Just like I reviewed over here, right? Okay. All right, so just plug in. There's the A. Of course, the A itself is a complex vector, but not a function of time, of course, right? But the time comes in when you say real part of that times e to the j omega t. Now, perhaps the easiest way to take the real part is just expand it out and use Euler's identity for e to the j omega t. So it's cosine omega t plus j sine omega t. Now, it's obvious that when you multiply here, you'll get four terms altogether, right? But two of them are real and two of them are imaginary. And remember, the rule says take the real part. So real part comes from what? X hat cosine. Remember, X hat and Y hat are real, of course. So X hat times cosine, that's real. Now, J times J is -1, right? So this is going to be real. It's going to be negative Y hat sine, right? But then you can see, for example, this one times this one's going to have a J in it. This one times this one's going to have a J in it. So ignore them, right? You're just taking the real part. So it just comes from this times this and this times this. So there you go. There's the vector in the time domain. There's the final answer. Okay. All right. And if I want to go backwards, I don't have to, but if I want to go backwards to the phasor domain, I would say cosine omega t is just, it's got a phase angle of 0. So cosine omega t going backwards to the phasor domain is just what? What complex number in the phasor domain corresponds to just cosine omega t? I mean, cosine omega t, okay. Maybe it helps if I write it like this. 1 out in front, cosine omega t plus 0. That help? What's the magnitude? What's the phase angle? 0. Okay, so the phase domain would be 1 e to the j 0 radians, which is just 1, right? Right? And that agrees with where we started. 1 out in front of unit vector x, right? Okay, just as a sanity check, what about sine omega t? Now you may remember this trick. Sine of x is cosine of x minus pi over 2. Remember that trick? So this would be cosine omega t minus pi over 2. Or again, 1 out in front, times cosine omega t minus pi over 2. Okay, so what's the magnitude? What's the phase angle? Okay, so the phasor would be 1 e to the minus j pi over 2. In other words, in the complex plane right here. So that's going to be then minus j, right? And that corresponds, but remember it says minus y hat sine omega t, right? Minus, so two minus signs, and that agrees with what we got up front, right? Plus j y hat, right? Okay, good. Just doing the sanity check, that's all. Now back where we started. Okay, so we've answered the problem, but let's kind of interpret it physically a little bit. Now, one interesting thing to take note of is if I take the magnitude of this vector in the time domain, square root of x squared, x component squared plus y component squared plus z component squared, which isn't any. So I just get this right here. So square root of cosine squared plus negative sine squared, which doesn't do anything, the negative sign. And of course, cosine squared plus sine squared is 1. Now, this is the interesting thing here, really interesting. Okay. And it's because of this j here. Okay. Notice that as a function of time, the magnitude does not change. It's 1. So if you graphically draw the vector A, the red arrow here, it's always going to be a vector that points out to unit 1 magnitude. So the tip of it's always going to stay on a circle of radius 1, right? Okay. But what does it do as time changes? Well, maybe it's helpful just to plot out a few points. So let's say you start with omega t equals 0. Sine of 0 is 0. Cosine of 0 is 1. So at time 0, you just have x hat. So you're right here, right? Omega t equals 0, right? Just right here. Okay, what about omega t equals pi over 2 radians? Cosine would be 0. Sine would be 1. So negative y hat. You're right here, right? Okay, let's do one more. Omega t is equal to pi. Sine is 0, cosine of pi is negative 1, so negative x hat, so you're right here. So you see what's happening? Here to here. You see that? So the vector is staying on a circle, and it's rotating clockwise in time. Okay? Now, it's not too difficult to prove that it's actually rotating at a constant angular velocity. Okay, how could I prove that? Okay, let's say the vector has some tilt angle up from the x-axis. Let me just call it theta. Okay. Okay, now from trigonometry, tangent of theta would be vertical over horizontal component. So that would be AY over AX, right? Supposed to be, sorry, it's supposed to be hand squared fine. Okay. Now, if you look at the y component here over the x component, don't forget the negative sign. Okay, that's going to be negative sine over cosine, so negative tangent, right? That's going to be negative tangent omega t, right? Now, tangent is what we call an odd function, which means the minus sign can be put inside. You know, for an odd function, if f of x is an odd function, then f of negative x is negative f of x, right? So we can say that this is tangent. Here, tangent theta equals tangent omega t minus omega t. What's the conclusion? Theta is equal to minus omega t, right? Or if you like, you could say the derivative of theta with respect to time is equal to minus omega. And then it makes it more obvious that it's rotating at a constant angular velocity of omega, but there's a negative sign there, so that means it's going clockwise. That make sense? Okay, so it turns out it's rotating on the circle clockwise at a constant speed. Kind of interesting. Okay, now it may not be obvious yet, but this example has great relevance for later in this semester when we talk about waves going through space, because this is going to correspond to what's called a circularly polarized wave. Okay, circularly polarized waves are very, very common in wireless communications. Of course, not everything is circularly polarized. Probably what's coming out of your cell phone is probably going to be linearly polarized. Your antenna has a fixed direction, so it sends out a wave polarized in that direction, right? But what's coming from like a GPS satellite is a right-handed circularly polarized wave. In fact, most transmission from satellites is circularly polarized. Okay, and we'll explain more details about why we like circular polarization later, and that'll be a topic later. But I just want to point out this has great relevance for a circularly polarized wave. Just to build on that a little bit, let me. Again, I don't go into too many details. It's going to be talked about later in the course, but let me just give you a little bit of a taste of that. So about the circularly polarized wave. Now, later in the semester, we're going to prove that if you have what's called a plane wave propagating through space, like a wave coming from a satellite or something like that, and it's circularly polarized, then it could look like this. Now, it's got two components, X and Y, and the third component that's missing, Z, would be called the direction of propagation, the direction the plane wave is going in or carrying power. And of course, it's propagating at the speed of light because it's a plane wave going through space. Okay. Now, don't worry about where this equation comes from. That'll be solved for later in the semester. Let's just pretend that's the electric field as a function of time and distance Z. There's no variation in the XY dimension. That's characteristic of a plane wave. It only varies in Z direction, the direction the plane wave is propagating in or traveling in. Okay, now let's just think about this for a second. See how it relates to the previous example. Okay, first of all, what's going to happen if I keep the position Z? That's like you're an observer. You can observe this wave any Z you want. The simplest Z to pick is probably just Z equals 0, right? So if I just fix Z, let's just call it this point here, Z equals 0. If I pick Z equals 0 and look at things in time, I'm just going to take this equation, put Z equals 0, so just forget the KZ term. And it's obvious you get this, right? Wow, that's exactly what we had here, right? So a fixed observer, here you are with your, receive antenna or something, looking at this wave going by you. Maybe it's coming from the satellite in space and you're here standing on Earth and you're looking at the wave going by you. You're going to see this wave that's rotating just like this one did clockwise. So you're going to see a wave rotating clockwise. Now, by the way, let me ask you this question. I don't want to redo this example, but what do you think would happen if I would have changed this to a plus sign? Yeah, it's just going to rotate the same velocity with counterclockwise. Right, good, okay. Keep that in mind, okay. Now, what I've actually got plotted here is what's called, I call it a snapshot of the wave. If we had a magical camera and we can take a picture of the wave at one fixed instant of time, that's what a camera does, right? And look at the electric field plotted versus Z at one time, this is what it would look like. And I'm just going to call it T equals 0, okay? So you're seeing this electric field vector, okay, in other words, this thing here, but you plot, so it's different Z's, but at T equals 0. Let's see if it makes sense. Okay, in my snapshot, I'm letting Z change in this picture, but T is fixed at 0. So this is going to be cosine minus KZ, but cosine doesn't care about plus or minus, right? It's an even function, so just cosine KZ. Here, if I let T equal 0, I'm going to get sine of minus KZ. Sine is an odd function, so that'll be minus sine KZ. But it cancels a second minus sign, so plus, right? Everybody see the algebra? Okay, just simple algebra there. Now, this looks the same thing as this, what I did in my example, right? Except for two things. There's a plus instead of a minus, and it's KZ instead of what I call omega t, right? So this is showing the evolution of the wave for a fixed time as Z progresses, as opposed to this, which is fixed Z and time is progressing, right? Okay, so let's look at this a second. So as Z increases, I go along like this, Z is increasing, which way is it rotating? So time is fixed in my snapshot, right? That's my snapshot, time is fixed, but I'm changing Z from here to here to here to here. It obeys this equation. So now what you know from that example, which way is it rotating? Counterclockwise, right? Because of the plus sign. Now, do you see it? Look at this. Here to here to here to here. Do you see how it's rotated counterclockwise? Okay. Now, for the grand finale, let's pretend you're standing here on Earth, measuring electric field. It rushes by you coming from the satellite. Now I need a motion picture. I don't have one. So now you got to use your imagination. Imagine this is animated. So this wave is now traveling. It's going at the speed of light. Let's slow it down. So imagine it's traveling like this. So if you're fixed here, it's equal 0. First, you see this guy rush past you. A little bit later time, this one, then this one, then this one, right? Can you visualize that? So which way have you observed the field rotating? Clockwise. Bingo. Matches perfectly with the math. You see that? If you got that visualized, you visualize a circularly polarized wave coming from a satellite going past you. Okay? Kind of neat. Anyway, our purpose isn't to get too much into circular polarization, but just it's a nice, beautiful example that illustrates the vectors in time domain. Okay, anyway, on now to the review. Now remember, in this set of notes, we're still kind of more or less reviewing basic stuff here. So this is a review of time average of time harmonic quantities. Here's a good old sinusoid. Now, of course, a sinusoid by itself has no average. This is my symbol for average value, which means you integrate over a period and divide by the period. Period is like this, one of the frequency. Now, of course, if it's a pure sine wave, sinusoidal function is no average value. The plot makes it obvious, right? So a period is like this, going from here all the way up to here, right? That's a period, equal positive, equal negative, so it's 0. To get something interesting, we can't just take the average of one sine wave, we've got to do something else to it. The simplest thing we can do is square it. Is the square of it, right? Now here's a helpful identity from trigonometry, okay, that applies for expanding cosine squared. I'm just going to use this identity where x is just omega t plus phi. The identity calls for a factor of 2, okay? Now notice you have a half here, and of course, integral of a half is just going to be a half times the time interval of which is called the period, right? That's where this term comes from. The rest of it is a sine wave. Now it's a sine wave that happens to be oscillating at twice the frequency of the original sine wave, and we square it, now it's a cosine 2, right? Okay, but still, the average is going to be 0. And so that doesn't contribute. So we just get the term coming from the 1/2, and simplifying the math a little bit, we get a squared over 2. So the simplest way to remember this is if you square a sinusoidal signal, the average value is just 1/2 the amplitude squared. That's the easiest way to remember it. Okay. Now, to be a little bit more general, rather than just taking one and squaring it, let's say I have 2 different sine waves. Okay. If you want to relate it to circuit theory, you can think of one as being a voltage and one as being a current. Okay. Just to visualize it. Okay, so anyway, here's one and here's the other. They both have different magnitudes, different phases. Okay, now it's helpful, and here's the time average. Okay, again, integrate over the period, divide by the period. I factored out the AB constant. Now we'll use this trig identity. It's perfect. It's for cosine something times cosine something, right? So this is going to be my x. This is going to be my y. The recipe says first subtract. Now when you subtract, the omega t goes away, right? So you just get alpha minus beta. When you add, then it doubles, right? So you get like this. Again, same principle. It's a sine wave, twice the normal frequency, but it's still a sine wave. Average value is 0. So you only worry about this term here, which integrates out to that constant times the period. The periods cancel, so we just get this. Okay? Now, let me just put that on hold for a second. I mean, that's the answer, but let me just kind of put it on hold for a second. I'll come back to it in just a second. Now remember, I'm calling one voltage and one current, okay? Now let me consider then, in the phasor domain, what happens if I take voltage phasor times the conjugate of current phasor? All right, so time domain, remember magnitude phase, right? Magnitude phase. So here's voltage phasor A, voltage phasor B. You know what the conjugate does. Phase angle gets replaced by its negative. So we get like this. And then we take something interesting and useful happens if we take the real part of VI conjugate, the real part, remember Euler's identity. So that's cosine. Okay. Now it looks very, very similar to what we just did on the last slide. The right hand is this, right? The right hand side is this. Well, it's the same thing here, except this had a factor of 2 in it, right? It's almost the same thing. All right. So this is the real part of VI conjugate phasor. And from the last slide, we have this. Okay. So what is it that we need on the right-hand side? Well, let's take the 2 across. So it's this thing, with a half. So we can say that this thing right here, or we're going to say this thing right here is 1/2 times this right here, which is the real part of VI conjugate. It's the best way to say it. Okay. Time average of voltage times current is 1/2 times the same thing as what we have right here. Okay. All right. So, and as you know from circuit theory, if we just say 1/2 VI conjugate, circuit people call that the complex power. I know you know that already, right? That's the complex power. So the time average instantaneous power is the real part of the complex power. And of course, the imaginary part of 1/2 VI conjugate would be what? What do we call that? What's imaginary power with units of VARs, right? Okay. Now we're going to see something very, very similar in a minute when I get to the Poynting vector. But anyway, just thinking of circuit theory, this is what we have here. Let's answer this question. I always write it like VI conjugate. Would it be valid to say I V conjugate? Is that valid or not? No. Why not? Louder? I'm sure I understood that answer. So now if I switch the conjugates, what am I really doing? But if I say I V conjugate, so I put the conjugate over here, if you think about it, what I've really done is this whole term in parentheses, I've taken the conjugate of it, right? I mean, what's the conjugate of this whole term in parentheses? It'll be V conjugate times I conjugate conjugate, right? But I conjugate conjugate is I again, right? Okay. So if I switch the conjugate position, I've really taken the conjugate of the term in parentheses. So think about it a second. Just call this whole thing Z. Is the real part of Z equal to the real part of Z conjugate? I think so. Remember what conjugate means? Yeah. So now what's the answer to the question in the box? Is it fair to put the conjugate over here if we want to? You're still saying no? Did my explanation make sense? So if I switch the conjugates, put it over here on the V, I've really taken the conjugate of the whole thing in parentheses. Does that affect the real part? No. Real part of Z is the same thing as real part of Z conjugate, right? So the answer to the question is, yeah, you can do that if you want. But people, for whatever reason, tend to put the conjugate on the I, right? No particular reason, but okay. Anyway. Does that affect the imaginary part, by the way? Yeah, yeah, yeah. So you got to be careful. The VARs would change, right? So if you have like passive sign convention going into a circuit, and you say, you know, VI is going to be the power going in, then you got to be consistent. So then you want to put the conjugate here to get the VARs right. Get the VARs right. Okay. Anyway. So now all of this ports over to vectors. Now that we've already talked about vectors and phasor vectors, let's just give an example. This is very meaningful in EM. This would be what's called the D vector and the flux density vector dotted with the E vector, the electric field vector. Okay. And each one could have all three components. So the dot product is going to look like this in general. Okay. Now for any one of them, you got 6 quantities here. For any one of them, you know, like for example, the D vector, you can see it's the real part of the phasor times e to the j omega t. That holds good for D or E, either one of them. They're all sinusoidal. Okay. So now let's take the time average of one sinusoidal vector dot another one. D dot E, 2 sinusoidal vectors dotted together, take the time average. Okay. Now you're taking the time average of this whole thing in parentheses, and it's pretty easy to prove that that's simply the time average of one plus the time average of the second one plus the time average of the third one. Okay, just look at the definition of time average, and it's pretty obvious. Okay, and now you don't have any vectors anymore. This is just a sinusoidal function times another one. So it works the same way I just proved a second ago, right? Just like pretending like one is V and one is I, for example. So this is 1/2 the real part of phasor one, conjugate of phasor the other one. Same thing for this one, same thing for this one. Now let's factor out the 1/2, lump all the real parts together. So we get like this. And there's a very nice interpretation to this thing now, if you think about it. That's in the phasor domain, phasor D vector, which has components dx, dy, dz, dot the conjugate of E phasor vector. E phasor vector by itself has components ex, ey, ez, right? So we've proven that this is true. Okay, so here's a summary. So if you have 2 sinusoidal vectors and you dot them together and take the time average, it's 1/2 the real part of phasor one dot conjugate of phasor the other one. Okay. Now, I'm not going to do the same proof for this one, but if you want to do it at home, you can. Okay, but if you have two vectors in the time domain and you cross them, which is of course another vector, right? Then in the phasor domain, well, I'm sorry, the time average is written in terms of the phasors as 1/2 real part of one cross the other one conjugate. So it works exactly the same way. Dots or crosses, it works the same way. Very nice. Okay. Again, for any one of these, you can always back from the time domain comes from the real part of phasor domain, e to j omega t. Okay. So taking time average is easy to do once you have the phasor vectors. That's the moral of the story. You have the phasor vectors, it's easy to take time averages. Okay. Okay, let's go one step further and relate this to practical stored energy. Now, we'll go over this a lot in 3318, and you have access to the class notes on 3318, remember, if you want to read that. But anyway, I'm just going to take this from 3318. In that class, we learned that the energy density, stored energy, okay, joules per cubic meter, stored in an electric field is 1/2 d dot e. So maybe you have like a capacitor, like a perovskite capacitor, you charge it up with a battery, it's got an electric field between the two plates, it's storing energy, right? The energy density in joules per cubic meter is given by this formula here, 1/2 d dot e. Okay. Now, of course, this could be a static electric field, or it could be changing in time some crazy way. But let's go ahead, for our purposes here, assume that everything is sinusoidal. Okay. Like, for example, this capacitor was connected to a sinusoidal voltage source. So things are changing sinusoidally, so the electric field between the plates is changing sinusoidally. Okay. And then we can use everything we just talked about. So the time average energy density is, I just take this and put the time average symbol, right? And use what we just proved a second ago, right? So 1/2 real part of phasor one dot phasor the other conjugate. Okay, so the time average is 1/2 real part of phasor one conjugate of phasor two. Now the formula from 3318 already had a half there, right? So there's two halves. This one is from the formula from 3318. Okay, but this half is coming from this, right? So notice there's a net 1/4. So if you want time average stored energy density in a capacitor that's varying sinusoidally, notice the formula is going to be 1/4 the real part of d phasor dot e phasor conjugate. Okay, and of course, if you had some volume, in this region between the plates, you have to multiply by the cubic meters because this is density, right? Joules per cubic meter. And that would give you the time average energy in joules stored inside the capacitor. That makes sense? Okay, so it's a little kind of tricky, but remember that in the phasor domain, and you're looking at stored energy, there's not a half, there's a fourth, because you already have a half already in the time domain. That's the way it works from 3318. Okay, anyway, same thing for magnetic field. Again, from 3318, we studied that the energy density in the magnetic field is 1/2 b dot h. This is called the magnetic flux density, and this is called the magnetic field. So the time average, we have a fourth there. But now here's the one that's probably going to be the most important to us at all. And this is really talked about in notes 5. There's a whole set of notes 5, that's on the pointing vector, the pointing theorem. Okay, so it won't be too much longer before we get to it. The pointing vector is one of the most important vectors in EM because the pointing vector is the power flow vector. It's telling us what the power flow is in an EM field. You might have an EM field surrounding your cell phone antenna or in your microwave oven, near a power line, anything. The pointing vector tells you the flow of power in the electromagnetic field. So one of the most important vectors in all of EM. That's why it deserves its own set of notes, okay? We'll get to that later. But anyway, just looking ahead in the time domain, see, this is supposed to be that hand script SF again, okay? It's the symbol for the pointing vector is S. Capital S, but that's what it looks like in hand script SF on. Okay, hard to recognize, but it's supposed to be an S. Okay, but anyway, in the time domain, as we'll see, it's defined to be E vector cross H vector, electric field vector cross product with magnetic field vector. Okay, So remember, I said dot and cross work the same way, right? Okay, remember that from a second ago, right? So we have like this, right? This is the pointing vector in the time domain. If you take the time average of it, 1/2 real part E phasor cross H phasor conjugate. Okay, so there you go. So the time average power flow in any EM field, assuming that E and H are very sinusoidally, that's what we're assuming all this time average stuff, is going to be 1/2 the real part of E cross H conjugate, phasor E, phasor H. Now, so this is a vector. The direction of it is going to tell us the direction the power is flowing in space. Now, for example, a wave is coming from that satellite going this way, so the power is flowing in that direction, right? The direction is the direction of the power is flowing in. But then the time average tells us the watts per square meter flowing in the wave. But we'll prove that in notes 5. So it's a watts per square meter flowing in the wave. Okay. Now notice the real part. If I just say, if I forget the real part and I say 1/2 E cross H conjugate, that's going to be a complex vector, right? Question. Think of analogy of circuit theory. 1/2 E cross H conjugate. So that's going to be a complex vector. What do you think I'm going to get if I take the imaginary part of it? Any guesses? The real part gives me watts per square meter flowing in space. Think of circuit theory, right? Complex power, 1/2 VI conjugate, real part is watts, right? But now it's watts per square meter of a wave. So in circuit theory, remember, I have 1/2 VI conjugate. The imaginary part was what again? VARs, the reactive power of VARs. So what do you think I'm going to get if I take the imaginary part of 1/2 E cross H conjugate? The VARs per square meter flowing in our wave. Right. Exactly. Good. Okay. All right. Just setting you up for notes 5 later. Okay. Oh, okay. We're at the end. All right. All righty. So well, this is kind of a mathematical set of notes. So perhaps not the most exciting. But think of it as like, medicine, it's still good for you, right? So this is like a review of vector calculus. Now, for those that have already had 3318, you probably don't need to see any of this, because in 3318, we do vector calculus in a lot more detail than this course, right? And all the 3318 notes are available to you again, right? And also it's all in the book. But it's so important, it sets us up for the entire rest of the semester. So I feel like it's worthwhile to at least spend a little time reviewing it. Okay, so bear with me. All right. Hopefully it's a review. Hopefully you already know all the stuff, but hopefully it's a review. But anyway, so I think this is already mentioned in the syllabus. Here's the actual website on the engineering course server, or where you can go to actually find all the 3318 notes if you want to see them. And I'll just point out that these 3 notes in particular might be of interest to you, because they talk about the main components of vector calculus, the divergence, the curl, the gradient, the plot. And of course, you can also consult your regular textbooks or these ones on reserve in the library, whatever your favorite book is, right? They'll talk about it. Okay. Anyway, so let's review the del operator. The del operator is defined in rectangular coordinates. This is the definition symbol, remember? It's defined to be x hat partial x plus y hat partial y plus z hat partial z. Okay. Now, you probably are familiar with the term operator, but there's a note here, footnote. An operator is something that operates on a function to return another function. In other words, an operator doesn't have a value by itself. An operator operates on a function to return a function, right? So if I give you a function like sine of x, that's a function, right? You give me an x, sine x returns a value, right? An operator, like in calculus, like the derivative operator. So like in simple calculus, we have the build derivative operator d by dx, right? We know that is the derivative operator, right? I ask you what's the value of it. Well, there's no value, right? It operates on a function and returns another function. If it operates on sine x, it gives me back cosine x, right? It's an operator. That's what operator means. Now, the del is like a 3-dimensional version of that. Right? It's got partial derivatives and then the unit vectors here. So it's a vector operator, as we call it. Okay, the rule is when you apply del onto a function, and because it's a vector operator, there's different ways you can apply it to a function. You can put it right on a function, you can dot it with something, you can cross it with something, if that something's a vector. There are different things you can do with it, right? But the rule is you just kind of treat it like any other vector, even though this is not a value, it's just a derivative. But the rule is just treat it like any other vector. So for example, and the wonderful thing about del, is almost no matter what you do with it, you know, put it directly on a function, dot it with something, cross it with something, you get back something extremely useful in vector calculus. So it's amazing. Okay, but anyway, so gradient comes about by just taking del and putting it right on a function. This is some function phi. Okay, in 3318, we think of this as the potential or voltage function, but it could be any function, right? So just take del and put it right on phi. Just put phi here, and every operator, every derivative just goes right on phi. So there you go. All right. So, and that's what's called the gradient. If phi is a scalar function of x, y, z, you can see that this is going to be a vector function, right? Gradient is a vector, right? Gradient is a vector function. A gradient of a scalar function returns a vector function. Okay, now I'll review the physical meaning in just a minute. But right now I'm just kind of going through the math, okay? The Laplacian is denoted by this symbol, del squared. It's kind of a cute notation, del squared, because people think of it like this, del dot del. Now remember, del is kind of treated like any other vector. If I have a vector with three components, you know, A, B, C, and I say vector dot itself, you know, what is that going to be? Just pretend it says A here, B here, C here, right? Like just pretend it's a regular vector for a second. And I say dot it with itself, what's that going to be? It's going to be A squared plus B squared plus C squared, right? Okay. And so if I think that way, del squared is going to be this times itself, second partial of x on partial of x, so second partial of x. This one on itself, so second partial y, this one on itself, so second partial z. So this is really what Laplacian is, Laplacian of a function. Okay, this is the symbol for it, but it can also be in a kind of a cute way said to be del dot del, because if you think about del dot del, it really means this, right? Like I just explained. Okay, so if this is a scalar function, like a voltage function, then Laplacian, of course, is also a scalar function. This is one of the most important things we do in electrostatics, like in 3318, because we learned there that if this is a voltage function, potential or voltage function obeys the Laplace equation, which means del squared phi is equal to 0. But anyway, so that's the Laplacian. Now, two more important things. And now these important things are coming by not working with a scalar function phi, which could be like a voltage function, but instead starting with a vector function. And I don't care what this vector function is, but let's just call it A, some arbitrary vector function. Remember, still a function. That means, you know, AX, AY, and AZ are still functions of X, Y, and Z, right? So as you move around in space, this vector is changing, right? So it's a vector function. I don't keep writing that, but you can put, you know, parentheses X, Y, Z if you're in here, right? It's a vector function. But anyway, divergence comes about by taking simply del, here it is again, definition of del dot the vector function. Okay. And then curl, as we call it, comes from taking del cross it. As it says right here on the next slide, this one's kind of obvious. This one's not quite so obvious, but the next slide, I'll give you a few more details there. Okay. I also want to point out that I'm limiting my discussion here to rectangular coordinates just for simplicity, but everything is derived in the books, especially the Hayton Buck books. It's got a really good appendix which does all this derivation, and it does derivations both not only rectangular but cylindrical and spherical. I strongly encourage you to read that appendix in the Hayton Buck book if you really want to brush up on derivations. If you don't like it, fine, but it's a really nice appendix there. But anyway, I'm limiting myself here just because of time. But anyway, let me give you a couple more details about these two guys here. So divergence and curl. Now notice divergence of a vector function is a scalar function, right? There's no vectors here. Curl of a vector function, if you believe this formula for a second, curl of a vector function is obviously another vector function. Okay. All right, just a few more details. Okay, a few more details just to justify those equations. So first one, I said del dot A is equal to this. Where'd that come from? Okay, here's del, here's A. This one's pretty simple, right? so most of them are going to be 0. X hat dot y hat is 0, for example, right? The only ones that survive is this dot this, this dot this, this dot this, right? And of course, x hat dot x hat is 1, y hat dot y hat is 1, z hat dot z hat is 1. So this just goes directly on this. Remember the rule, you treat del like any other vector, except finally this is an operator, not a number. So when it comes over on this guy right here, what it really means is partial of ax with respect to x, right? When this comes over on here, it means partial of ay with respect to y. When this comes over on here, it means partial of az with respect to z. So that's the proof of this equation, right? Okay. What about this messy looking one? The claim is that's the curl, what you get when you take del cross A. Okay, here's the details if you want to see it. So del, again, definition of del operator, cross or arbitrary vector function. And I'll just use the good old determinant rule for taking cross product. Because remember, you just treat this like any other vector, right? It's like, vector 1 cross vector 2. So remember how that works from calculus. You make the determinant in the first row, x hat, y hat, z hat. And normally this would be the components of the first vector. But remember, they're not numbers, they're the operators, right? But you treat it like any other vector. So the second row is the components of the del, which is really derivative operators. And then the third one is the components of the third vector, which is this thing called a vector, right? So ax, ay, z. And then just expand it out. You know how to do that, but just as an example, remember, don't forget the plus minus plus rule. So example, the first one would be unit vector x, cross out row and column. So it'd be this times this, minus this times this. But what do I really mean when I say this times this? I really mean this goes on this. So partial of az with respect to y, and then minus this times this. So what does that really mean? Partial of ay with respect to z, right? And then et cetera, et cetera. Okay, remember that from calculus? Okay, good old determinant rule. Okay. All right, so that justifies this. Okay. So those are, now remember, I'm limiting formulas right now just to rectangular coordinates. Okay, now I'll get to the physical interpretation in just a second. How am I doing on time, by the way? Okay, good. Okay, but before I get to that, now that we have just gone over the definitions of all those interesting things, let me give you a couple identities that will turn out to be important later in the semester. Now in this slide, I'm giving you what I call 0 identities. At least that's what I call 0 identities. Why do I call them that? Because the right-hand side is 0. Okay, so 2 0 identities. And probably simple enough, you can memorize them. They're pretty easy to memorize. Okay, the first one says divergence of any curl, A is an arbitrary vector function. Okay, divergence of any curl is 0. Second one says curl of any gradient is 0. Okay, now remember, gradient is always taking del of a scalar, right? This is a scalar function, this is a vector function. Okay. You see why I put vector 0 here, by the way? Because curl is a vector, right? Divergence is not. Okay. Now, I think not in homework 1, but it might be in homework 2. You're going to be asked to prove some of the identities, maybe both of these or some of them. Okay. Let me make a note on proving identities. Okay. Now, if a vector identity is true, then it should remain true in any coordinate system. Okay. So when you prove a vector identity, like for example, this first one here, you're free to prove it in any coordinate system you want. If you prove it in any one coordinate system, it should be true in any coordinate system. Okay. But normally the easiest coordinate system to work with is rectangular coordinates, the formulas I just showed you, right? So if I want to prove that this identity is true, I can use what I just showed you, the formula for curl, and then the formula for divergence, use those formulas in rectangular coordinates, show in rectangular coordinates this is true no matter what A is. And once I've done that, I'm done. It's got to be true in any coordinate system. Okay, that makes sense? Okay, I'm not going to prove that here, but I think on homework 2, you'll have the opportunity to do that. Okay, anyway, divergence of a curl, always 0. Curl of a gradient, always 0. No exceptions. Okay. Okay, here's another identity. It looks kind of messy. Why in the heck would we need this? Well, just take my word for it. In notes 5, when you do the pointing vector, the pointing theorem, this will become instrumental in the development of the pointing vector that we just talked about. So, where does the pointing vector? I said the pointing vector is the power flow vector, right? Where does it come from, though? Well, it comes from Maxwell's equations after doing a little bit of vector calculus. And this is going to be one instrumental identity that we need in those 5 to do that. Okay, but anyway, for right now, just consider it to be identity. All right. It's dot divergence of cross. You have 2 vector functions, A and B. You take a cross, that's going to be another vector function, and this is its divergence, right? So the left-hand side is going to be some scalar function. Now, anyway, you believe the identity, divergence of a cross product is written like this. B dot curl of A minus A dot curl of B. Okay, I mean, all I can say is if you expand both sides, you can prove it. Again, it's probably easy to prove in rectangular coordinates. Okay, anyway, there it is. Keep it in mind for those 5. Now, here's something that's going to be useful way later in the semester when we talk about solving for waves propagating through space, coming out of antennas, on transmission lines, and what's called waveguides. When we talk about propagating electromagnetic fields, this will be a very interesting identity that'll be useful for us later in the semester. Okay, probably not meaningful for you now, but it'll be useful later. Anyway, let me just introduce it. Now, okay, first of all, let me just backtrack for just 1 second, if I could. I've already defined Laplacian. Now remember, this is what I'll call the usual Laplacian. This is a scalar function like voltage function. Okay, and Laplacian operates on scalar function to give back another scalar function. So don't confuse that with what I'm going to do now. Right? This is the normal, regular scalar Laplacian. I'm introducing something a little bit more exotic, something called vector Laplacian. Now, vector Laplacian is something that operates on a vector. So here's an arbitrary vector function. I'm taking vector Laplacian of it. And what the heck is that? Laplacian of a vector. What the heck is that? Well, remember, this is the definition symbol. This is the definition of vector Laplacian of a vector function. Gradient of its divergence minus twice its curl. Why in the heck do we want to do that? Right? That's a crazy definition. Why in the heck would you want to use that? Well, as it says in the box, and you got to take it on faith right now, this will be very useful for later in the semester. And in particular, it's going to be useful for deriving what's called the vector Helmholtz equation, which comes from Maxwell's equations, which is the fundamental differential equation that electromagnetic fields obey in the phasor domain. Electric field, phasor, magnetic field, phasor, they obey something called the vector Helmholtz equation, which we're going to solve. That's how we're going to solve waves going through space and so on. But anyway, in order to do that, in order to get that, we'll end up using this identity later. So it's very helpful for a later derivation when we show that the fields obey the vector Helmholtz equation. Okay, now let me just give you one more interesting thing about the vector Laplacian. Now, this is not obvious either, but let me give you one interesting thing about the vector Laplacian. Now, this is the definition of it. This is the definition of it. But let me give you one interesting property of it. Now, this property holds in rectangular coordinates, not cylindrical or spherical. But in rectangular coordinates, if you take this right-hand side and expand it out, you can show that it can be written like this. So the vector Laplacian of a vector function, is x hat times regular scalar Laplacian of the x component of A, plus y hat times the regular scalar Laplacian of AY. And finally, for the z component, you see that? This is that regular Laplacian, right? The scalar Laplacian, right? Because like I said, del squared phi, right? Remember, ax itself is not a vector, right? Ax is a scalar function, right? This is like my phi function. So regular Laplacian, x hat front, the whole thing's a vector. So of course, this is a vector. But it's not obvious, but this is true. This is the definition, right? If you expand it out rectangular, you can show it to be this. And maybe you will on homework too. We'll see. Okay? But that'll be very useful for later in the semester. Why? Because it's so much nicer to work with scalars than vectors. So if I say, for example, that electric field phasor vector obeys the vector Helmholtz equation, and I know that this property is true, now I can work with scalar Laplacians. If I know a plane wave has a component that's called Ex, then I know that I can reduce down to scalar Laplacian, and it's a lot easier to work with, a lot easier differential equation to solve because there's no vectors. Okay, probably saying too much. We'll do all that later in the semester. But anyway, just keep it in mind for the future. Okay, anyway, now I'm going to end the review here by just going over, reviewing, hopefully, the physical properties of these different things, gradient, divergence, and curl. Okay, so I've given you the definition, right? I've given you the formulas in rectangular. But now I'd like to just read physical properties and kind of like why we like them, right? Some of the nice physical properties. Okay, gradient is usually talked about in calculus, but let me kind of review that. Okay, here's the setup right here. Here's some arbitrary point in space. R vector is a shorthand notation for just x comma y comma z. It's what we call the position vector or observation point in space. And then I'm going to march along some direction called unit vector L to get to a nearby point. The little displacement vector going from start to finish is called the dr vector, and the ending point is called r plus dr. Okay, so that would have components x plus dx, y plus dy, z plus dz. The little displacement vector dr has in three-dimensional space components dx, dy, dz, right? Okay, another bit of notation. The magnitude of this little displacement vector, this blue dr vector, I'll call dl. In other words, the little length in meters, that little dr vector. So the dr vector, this blue dashed line, this dr vector, this displacement vector has a length dl and a direction called unit vector L. Okay, so if I want, I can say dr vector is dl times unit vector L, right? Magnitude and direction, right? Okay, now I'm interested in knowing how a function phi, and it could be a voltage function or something else, I don't know, but some function phi, and I'm interested in knowing how the function phi changes if I go from the start, called r, to a very nearby, close by point called r plus dr. That's the goal. Okay. Now, if I was just in one-dimensional space on the x-axis, then how a function f of x changes is just described by the derivative, right? Derivative of f with respect to x tells me how things are changing along the x-axis, right? So if I have a start point and here's a nearby point on the x-axis, what's the change? Derivative of f with respect to x times dx. Okay, but now I'm in three-dimensional space, so things are a little more general, and that's where the gradient comes in. So from calculus 3, I guess, we learned there that the change in phi, the differential change, d phi, in other words, phi here minus phi here, the differential change, right? Finish minus start, is given by, as long as it's a small displacement, is given by this formula right here. So that's, I'm not rederiving that, but that's in your calculus book. Okay. Now, what I want to point out here is that this formula from our calculus books can be written as the dot product of this vector times this vector. This dot this. It's pretty obvious, right? Because again, you know, the dot product, this one's going to dot to this to give you 1. And it's going to give you simply partial phi with respect to x times dx. That's the first one, right? Second one dots with this one to give this. Third one dots with this one to give this, right? But this is the gradient vector. So this is the gradient of the function phi at this starting point. That's what I mean by that. The gradient at the starting point, I'm going to symbolically represent it by this red arrow. It's got some magnitude, it's got some direction. I don't know what they are, but I'm just going to draw it like that. That's the gradient vector in red. Okay. This is what I call my displacement vector, the blue dashed line going from A to B, start to finish, right? Okay. So d phi, the change in the function going from start to finish, is approximately given by this. Okay. Now, this is what the mathematicians call the directional derivative. You may remember that term from calculus. It's the change in the function going from here to here divided by the distance I want. This, you know, the length here, dl. The rate of change, in other words, the rate of change, how the function is changing per meter step as I go in this direction, unit vector L. That's called the directional derivative, right? So it's like the normal derivative df by dx in calculus, except that stays on the x-axis. Now I'm going in three-dimensional space, arbitrary direction, right? So it's how things are changing per distance as I go in this direction, the blue arrow, unit vector L. Anyway, so I take this by d phi, right, and divide by dl. I just rearrange it slightly, group these two terms together, and this term in parentheses is unit vector L. Because remember, what's the dr vector? It's dl, the length, times the direction, unit vector L, right? Okay, so dr is unit vector L times dl. So anyway, so the directional derivative, the rate of change of a function, which each step I take in space, is given by the gradient dot unit vector L, the direction I'm marching in. Now, as I leave this point, going from my starting point to my final point here, it's my choice what direction I want to go in space. Totally my choice. Unit vector L is my choice. It's not my choice what the gradient is. You give me a function that defines its gradient. So at this point, the gradient is some red arrow, right? But I have the choice to march in any direction I want. Now, as I march in that direction, the rate of change of the function is given by the gradient, which is this fixed red arrow vector, dot my direction of choice. So, as an example, if I'm free to go in any direction I want in three-dimensional space, starting from this original point here, question: what direction would I want to walk in or march in space to make this rate of change as large as it can ever be? What direction would I want to march in? Give me the direction of the blue line here. What direction should it be in? What? Opposite the, why'd you say opposite? Well, okay, now there's really kind of two answers, because I can choose my direction, unit vector L, to make the function phi increase as rapidly as possible or decrease as rapidly as possible. I should have clarified. What direction do I want the blue arrow to be in if I want to make the function phi increase as rapidly as possible? That means I want this to be a positive number, right? And as big as possible. I want to maximize this, right? Remember, this is a fixed vector, this red vector. I can make this point any direction I want. What direction should it point in so that this dot product is maximized? Right, right. I mean, the dot product is really magnitude of this times the magnitude of this, which is 1, times cosine of the angle between, right? So I'm going to maximize when that angle is 0, right? Cosine is 1. Yeah, so if I march in the direction of the gradient, I'm going uphill as fast as I possibly can, if you want to call it that. With every step I take, I'm maximizing the function phi as rapidly as possible. But now, okay, back to what you were saying though. So if I want to go downhill as rapidly as possible, make phi decrease as rapidly as possible, what direction would I march in? Opposite the red arrow. What direction would I start in if I didn't want the function to change at all? Perpendicular, right? Good, you got it. Okay, good. Okay. Now on this slide, I'm finally showing you formulas in cylindrical and spherical. And again, see the appendix in the Hayton-Buck book, if you actually see a derivation, but you're not responsible for the derivation. Okay, but there they are. Okay. Now let me review the physical property, physical meaning of divergence and why we like that. Okay. Now remember, this kind of discussion and proof of all this is in the 3318 notes. Okay. Take a little cube. Okay. This is an illustration of some vector function. Let's just call it A again. It's got 3 components in general, right? And I'm interested in calculating the divergence at some point, which is the center of the cube. It's shown at the origin, but it doesn't have to be any point in space. I put a little cube about the point of interest. Okay, this little cube has this volume is shown here. And n hat means unit vector, n hat is the outward pointing normal. Like on this front of the face, this face of the cube, n hat would be positive x hat. On this face of the cube, n hat is positive y hat. On this face of the cube, n hat is negative y hat, right? Etc. 6 faces, 6 unit vectors, right? Unit normals. Anyway, you can prove this, that the divergence has this physical interpretation. Divergence at this point has this following physical interpretation. It's the limit as the cube shrinks down, the surface integral, this closed surface integral over the surface of the cube, in other words, all 6 faces, vector dot outward normal, and then divided by the volume. Okay? So sometimes this is called the flux of the vector function, the flux of the vector going out of the cube, out because we're taking outward normal. Okay? So the meaning of this is that this divergence measures the rate at which flux emanates out of the cube per unit volume, really. Okay? So the flux coming out of a cube divided by its volume. Now, if divergence is positive, so this integral is positive, then there's a net flux of the vector function coming out of the cube. Okay, so we can say that this point is acting as like a source of flux. If divergence is negative, then this overall integral is negative. There might still be flux coming out on some faces, but there's got to be flux going in on other faces, and more so the net integral is going to be negative. And if that's true, then there's overall net negative flux going into the cube. And I would say that that point in space is acting like a sink of flux lines. Okay. Now in 3318, we would think of the A vector as being the D vector, the electric flux density vector. And then this would be the flux going out of a cube. And this strongly relate to Gauss's law. Right. where the net flux coming out of a cube is going to be a charge enclosed inside by the cube. But anyway, that's the physical meaning of divergence. So if you have a positive or negative divergence, you can say that at that point in space, that the space is acting like a source of flux or a sink of flux. Now, to make it a little bit more physical, let's make it more concrete by saying this A vector is something that's really easy to visualize. Let's say it's the velocity vector of water. So this could be inside a bathtub or a river or something like that. But at any point, the water's got some velocity, and that's the A vector. That's what it means physically. Now we're going to visualize it. Now, if water is just flowing from left to right in the river, there probably wouldn't be any divergence. But here's something, may not be practical, but here's something you can do if you want to have a divergence in your bathtub. Take a lot of little small pipes, like straws or something, really skinny pipes, stick them all down here. And each one, you're going to inject water. Okay. Now, in the limit, you'd like each one to shrink in size, infinitesimal in diameter, and the whole bathtub is just filled with a continuum of little pipes or straws, right? But anyway, so they're all ending at different points. They fill up this entire volume where each one injects a little bit of water, right? Now, if I take a little cube and surround any point, here's the center point where I'm calculating divergence. Now, I'm going to claim that in this experiment here, this water vector velocity function A at any point in the bathtub has a positive divergence. That's what I'm going to claim. See if you can visualize that. So you have this little cube here. Does it make sense that if I take this little cube here, you're going to have a bunch of water, being injected from these little pipes or tubes, and you've got net water coming out of this cube, right? That makes sense. So I can move this cube anywhere around, right? So at any point in this region called the bathtub, I would say the A vector function has a positive divergence. Every point in the water is that it has basically the property of being a source. Water is bubbling out from all these little pipes. So I take any little volume I want anywhere, and it's going to have a net water coming out of it, right? You agree? Now, if every pipe was sucking in water, then I would say that at every point in the bathtub, this function would have a negative divergence, right? You agree? Now, if there's no pipes, and I just have water smoothly flowing on the bathtub, then there'd be no divergence because water would come into the cube, but then equally go out of the cube, right? So just water flowing at a steady rate has no divergence. So divergence is measuring not a flow rate, it's measuring the property of source or sink in the fluid, right? That's what it's measuring. Does that make sense? That's the physical way to think about divergence. There it is in rectangular, cylindrical, or spherical. Again, see the book, Peyton Buck, appendix if you want derivation for those guys. Finally, curl. Now remember, curl of a vector function is another vector function. That's the one tricky thing about curl. Okay. Now, curl, here's an arbitrary vector function. Here's just curl. That's another vector function. So that means it's got all three components. Now, one way to define any vector is to first define what the x component is and the y component and the z component. All right. So what I'm going to do is talk about, let's just pick one of them, the x component. And I'm going to claim that this physical property is true. Again, proof given in the 3318 notes or the books. Okay. Now let me go over what this formula means here. Okay. I'm taking the x component of the curl. And I'm claiming the physical interpretation is this. Take a little surface. It turns out the shape is arbitrary, but most people assume a little rectangle. So a little rectangular path, and it's perpendicular to the component of curl I'm measuring. I'm measuring the x component of curl. See my unit vector going in the x direction? Okay. And then there's a right-hand rule. Okay, so the thumb of the right hand, not the left hand, the thumb of the right hand goes in the direction that you're measuring the curl in, like positive x hat. And then the fingers of your right hand tell you which way to go around the little rectangular path. So you see that? Thumb coming out of the screen, fingers are going around counterclockwise. You agree? Right hand rule. That's the definition of the contour called CX, going counterclockwise like this, right? That's CX. So then the x component of the curl physically means you integrate around the boundary with the right-hand rule, vector dot dr, and then divide by the area, there's no volume now, it's area. Okay? And again, Turns out the shape, as I'm saying here, it's kind of arbitrary, but usually rectangular path is chosen for convenience. But there's something called Stokes' theorem I'll review in a second. It turns out, this is in the 3318 notes, but it turns out Stokes' theorem can be used to actually prove that the shape of the path is arbitrary. But again, most people just start by assuming the rectangular path. Anyway, now you do the same thing for calculating the x, y, or z components. So the claim is that this is true for all three components. So again, thumb is in x direction, y direction, or z direction. Visualize it. Thumb of your right hand. And notice in all cases, the integration sense is the fingers of your right hand. Now, this is what I'll call an exploded view, right? So I'm calculating the curl right here, but if I tried to draw three of these paths right on top of each other, it would look confusing, right? So if I'm calculating the curl here at the origin, say, then all these paths should be centered at the origin, just like this one was centered about the point I'm trying to take the curl, right? But again, exploded view just makes it more clear what the paths look like, but they're really all on top of each other because I'm calculating the curl right there. Okay, so that's one way to physically think about the curl. The components of it give these integrals going around in the direction of the fingers of the right hand, integrating and then divided by the area. Now, to make that more physical, I still wouldn't call this very physical, but to make it more physical, I'd like to introduce the curl meter, a little paddle wheel. Okay, it's got a axis or spindle, whatever you want to call it. And it's got veins sticking out. It's a little paddle wheel, right? Now it's got an axis, and you can point that axis in any one of these three directions you want: x, y, or z. Unit vector L is just a notation. It means your choice: x hat, y hat, z hat. Just to keep it simple, let's just pretend it means z hat. That's what the figure shows, right? The axis is vertical. So just pretend it's saying z hat. Now, imagine that I can measure torque on the paddle wheel. What's called TL. I'm pretending L means Z, so torque in the Z direction. Remember what that means from mechanics. So that means put the thumb in the direction Z, and positive torque would mean this thing wants to spin according to the fingers of the right hand, right? Remember that from physics? Negative Z component of torque means it wants to spin this way, right? So just pretend I can measure the torque T sub Z. It can be positive or negative, depending which way this wants to spin, right? That's my paddle wheel. And I'm going to claim that this paddle wheel is really kind of a nifty little way to measure curl. That's what I'm going to claim. Let's see how that works. So remember, I'm pretending L is unit vector Z. It could be any one of the three, but let's pretend it's Z. So let's revisit this equation right here. So Z component dot curl of curl dot Z. Here's that formula again, right? But the one thing I'm going to do different is here, I took a rectangular path, right? See that? Path CZ. But the claim was, shape doesn't matter. That's the claim, right? So let me take a circular path now. So it's the same formula as this right here, right? Except instead of using a rectangular path, I'm going to use a circular path. I'm measuring the curl right here at the center of the paddle wheel. So I've got the circular path, right? Now, so that's the formula. That's this formula. It's a circular path. Now, let's think about it just for a second. Now, remember, A is the velocity of the water. Remember that. Now, what the heck does this mean? I integrate around the path CL by the right-hand rule. So I'm going counterclockwise, remember? Just like this. Okay? A dot dr. A is the velocity of the water, dot dr, and along a circular path, dr vector is a little vector that says tangent to the path, right? Tangent to the circle. Now, when the water hits the vein here, okay, the velocity of water could have some arbitrary direction, right? But think about it. When the water hits one of these little veins, the velocity component of the water, the part of the water velocity that gives a force to the vein is going to be the part that hits it dead on. You know, the velocity vector can be resolved into two components: component that hits the vein dead on and a part that's tangent to the vein, right? The part that slides tangent to the vein doesn't give the vein any force, right? The part of the water velocity vector that hits dead on gives it the force and therefore the torque, right? Now, when you say A dot dr, remember, dr on a circle path like this, dr is staying tangent to the circle. So when you get to one of these veins, dr vector on the circle is perpendicular to the vein. So my claim is A dot dr is what we want. A dot dr is the component of the water velocity hitting dead on, right? So if you buy that, then it makes sense to say that the physical meaning of this integral is that it's proportional to the torque we're measuring. Okay? Now, we don't have to worry about those constant proportionality. This is mechanics course, we probably would, but we don't care about that. The important thing is the z component of the curl of the water vector is basically proportional in some way to the torque we're measuring. So if you want to know if the curl has anything in the x direction, y direction, or z direction, is there a component of curl in one of those three directions? Here's how you'd measure it. Take your little paddle wheel, take the axis, point it in the x direction, y direction, z direction, and measure the torque. If there's no torque, there's no curl in that direction. The stronger the torque, the more the curl is in that direction. Now, if you measure torque spinning according to the right-hand rule like this, you've got a positive curl z component, let's say. If it's going the opposite direction, your component of curl in z direction was negative, right? And same thing for the x and y directions. So really nifty, I have to put here, yes. So a very nifty way to actually make a curl meter, assuming that you're talking about water, right? If it's something like electric field, well, we can't really visualize it, but it's the same kind of idea and principle. I better quit here. So here's a really cute example, but I'll save it for next time. That kind of drives this home even more. All right, so anyway, if you want to read ahead, would you please start reading then in Maxwell's equations? Okay, so that'll be the main topic coming up for next week. Okay, Maxwell's equations. All right, thank you.
Yeah.